In this video, we're going to talk about types of chromatography, specifically thin layer chromatography, often called TLC. Now, we are going to talk about what is TLC, explain to you how it works, but mainly it's about interpretation again. Just like it is with gas chromatography, it is about interpretation of your results. And we'll go further to discuss this in the exam style questions video that follows this. But what is chromatography? Just to remind you, this is a method of separation that depends on the equilibrium between a mobile phase and a stationary phase. Now, the mobile phase is the solvent and the stationary phase is the solid that is on the plate, but we'll show you that visually now. So, as I said, stationary phase is that solid that's on this piece of aluminium foil normally, or a piece of plastic, okay? And then we have the mobile phase, which is the solvent, and can be a mixture of solvents. But what does this actually look like in the lab? So it's going to be a small square. You probably would have done it in GCSE using a piece of paper, but instead it's a piece of plastic with this solid, white solid over the top. We're representing it here as just this rectangle. Now that is the TLC plate with the solid stationary phase on the top. First thing we do, as we do in GCSE, is draw a baseline with pencil. We draw it with pencil so that it doesn't dissolve in the solvent when we're doing the TLC. We then spot our reactants onto the plate, okay? And in this case, we're doing our reactants, the mixture, the reaction mixture, and our final product. We have some sample of our final product that we want. We have the reaction mixture we're trying to do, and we have the reactants that we're starting with. And this TLC is used to monitor whether a reaction has gone to completion or not. Has it finished? If it's finished, we won't see any reactants left because we'll get close to 100% yield. If the reactants are still left, then there's still some reaction to go, for example. But we'll see that in a moment. Now, to run the TLC, you'll take this TLC plate, you'll place it into a beaker, okay, and you'll put your solvent below the baseline. So here is your solvent. Now, that is your mobile phase, and it's going to move up the plate. Now, to finish this off, we put a lid on top. That's to make sure that this space here is saturated with solvent, because if it's not saturated with the solvent as it goes up the plate will just evaporate off, and you'll get a horrible kind of bendy line. And often if you see a bent line like that going across, that means you didn't have the lid on properly. Okay, so anyway, let's run this TLC as it would happen in the lab. You'd normally put this in, then leave it there for, I don't know, somewhere between 3 and 5 minutes. And as you do that, the solvent will go up the plate. Now you take out the TLC when the solvent gets towards the top, and you write down again in pencil this line to where the solvent got to. As you can see, and we've coloured them in here to make them obvious, but in your exam there'll be black dots. Okay, you can see the reactants have got to this level, okay, and our product has got to this level. This is our reaction mixture, and you can see our reaction mixture has 2 different dots, which means, and they're at the same level as the final product and the same level as the reactants, which means that I have some reactants and I have some product, which means my reaction's not finished yet because I've still got reactants left. And you might decide to there, for example, leave your reaction going for a bit longer. It's a way of monitoring whether a reaction is finished, and also for monitoring the purity of the product. I can see my product here in the reaction mixture is not pure at the moment, okay, and may need some form of purification. Now, here we've now marked the baseline and now marked the solvent front, and we will use the distance between these two in our calculations of RF shortly. So let's get rid of the beaker, and as you get rid of the beaker, let's start talking about why does this separate. So the distance travelled by the compound is changed by the mobile phase and the stationary phase. So its interaction with each one means that it will go further up the plate or not as far. So if it's attracted to the stationary phase through adsorption, for example, if it's really attracted, it's not going to move very far. So basically we can say that this reactant here is more attracted to the plate, to the solid on the plate, the stationary phase, than the red dot is. The red dot is not as attracted because the solvent is taking it up the plate. Now, on the converse of that, if it's really, really not attracted, you should see it right at the top. And again, just to finish off, if it's really attracted, you should see it down at the bottom. And it's done through adsorption. Now, let's start to look at something called RF, which is how you interpret thin layer chromatography, or TLC. The RF reflects the distance of the compound up the plate relative to the solvent front. So at the start of this, you see we marked down where the solvent front was, we marked down where the baseline was, okay, which means we know the distance between those two. But we're going to visually show you how you do that. And you can use the RF that we calculate to identify the compound. For example, if it has the same RF, if you do 2 dots, and you calculate the same RF, it's with the same solvent, it's at the same temperature, it's on the same day, that's really important, okay, then you can roughly say that those are the same. You might have to do further tests to confirm, but you can roughly say that they are the same. So let's show you how you do it visually. So here's our trusty ruler, and I expect you to get your ruler out in the exam, and I'll put my ruler up against the dot, and then I'm going to mark where my distance the spot has got to, or distance the reactant's got to. Notice my arrow goes to the middle of the spot, okay, not the start, the middle. Okay, so that's a really important exam tip. Go for the middle, not the edges. Okay. Now, if we take the ruler away, and then we put the millimetre down. So we measured that, we just note that down for later. We now go for our final product and try and measure that. Put our arrow in again, going to the middle of the spot again from the baseline to where the final product got to, and that's 48 millimetres. And then our last one that we do, okay, is to look at the solvent front, because to calculate RF, it is the distance moved by the compound, which we've got. Here's our 2 compounds. The reactant's 27 millimetres, the final product is 48, so we can calculate 2 RFs, one for the final product, one for the reactant. And then we divide it by the distance moved by the solvent. So let's do the distance moved by the solvent now. So it's that arrow here. And if you look across on the ruler, you can see that that's 60 millimetres. Now we're going to put this all in the right orientation now and put it into our 2 calculations, RF, which is the distance moved by the compound, which is for the reactants, it's 27, for the final product 48, and divide it by distance moved by the solvent, which is 60. Let's do that now. Right, okay, so we've got an RF for the reactants of 0.45, and a really interesting thing is to say you can roughly know whether you're correct, because if you look here, you see it's roughly halfway up the plate in terms of the solvent front. So it's going to have an RF of around 0.5 because you're just dividing by the distance the solvent front went to. And you can see the other one is roughly in the right area as well. So you can do a rough check to check whether you're on the right lines. But that is how you calculate RF, and you can then use the RF to compare against others. So remember, if something has the same RF and has the same conditions, same temperature, for example, same solvent mixture, and so forth, and is done exactly roughly the same time, I say exactly roughly because I mean a couple of minutes doesn't matter, okay, at the same time, you can say that those are the same things if they're on the same, for example, level, and therefore are the same RF.